I grew up moving around all over the country, mostly in the South and the Midwest. I grew up in kind of a very conservative context. I was homeschooled. We listened to Rush Limbaugh a lot growing up. By the time I graduated high school, the only time I'd ever heard the word environmentalist or environmental was in the context of crazy radical environmentalist commies that are trying to take over and destroy the world. So I went to college at a big state school, Indiana University, had my mind blown by where my food came from. I became vegetarian for a long time. I kind of went down this rabbit hole of learning more and more and more about the state of the planet and trying to figure out what I could do about it. I got a bachelor's degree in environmental science. Didn't know what to do with it, so went to grad school. I studied complexity theory, complex system science in the context of ecosystems. So using complexity, like understanding ecosystem complexity. A lot of it's kind of BS, but I'm going to talk a little bit about it today. What I think is actually helpful for people like us trying to do things out there in the world. Got a master's degree in that. Didn't know what to do. Started down a PhD path. Started doing research. I was really lucky in that nobody was paying me to do anything, so I got to do whatever I wanted. So I got really interested in ecosystem restoration. How do we restore these ecosystems that are supporting this, our whole the human race. We're all supported by ecosystems. We're degrading those ecosystems. We need to restore them. How do we do it? Went down down the academic path. Came to this realization about our native ecosystems in the Midwest, which are oak savannas, very similar to out here. Totally different trees, but it's a similar form of vegetation, and sort of had some realizations that restoration needed to be done by people embedded in those systems. So that's kind of what I'm going to talk about today. This image right here, I just love. This is at Mark and Jen Shepherd's farm. I ended up dropping out of grad school right before I got a PhD. Moved in with Mark and Jen at New Forest Farm, started raising livestock, spent 2 years there. My wife and I have since bought our own place and are farming in southwest Wisconsin. But I'm going to talk about Savanna. So this is their place. It's a beautiful place if you ever get a chance to go. So another thing before I jump in here is that I'm going to move kind of fast because I've got a lot to get through to get to kind of the punchline at the end. And if you're somebody that needs to take notes to try to pay attention, then do that. But if you're don't take notes if you don't have to. I'd much rather you just kind of sit back and enjoy it, and I'll make the slides available to anybody afterwards. So if you're just trying to capture information, you can get that later. Just enjoy. So the Holocene is a period of time since the last glaciation, 12,000 years ago. Scientists call that the Holocene. And in North America, much of North America during that time after the glaciation was what we would call now an oak savanna. One of my ancestors, George Rogers Clark, he won the Midwest, the Northwest Territories, which is the Midwest, in the Revolutionary War. He was traveling through Indiana, chasing down the Brits, and he said, "This is the most beautiful country he's ever seen, large prairies with buffalo and other game, and these very groves of trees." And that was largely what our continent looked like. And even in the Northeast, where we think of it's more like hardwood forest, it was much more open hardwood forest. There was a lot of burning going along, keep things open. And then in California, the Central Valley and the classic oak savannas there. So savanna was largely a big part of savannas were a big part of the North American ecology, and for a really long time. But I'll get into that in a little bit. Aldo Leopold's one of my heroes. If you've never read Leopold, do it. It's worth it. Sand County Almanac's a classic. But he was the first director he helped form the UW Arboretum, which is an amazing place, at University of Wisconsin, where I went to graduate school. And in the inauguration, he's describing the oak opening, or that was a colloquial term for oak savanna, and how the grandparents used to talk about these beautiful stands of trees, orchard-like, park-like, which is not random, interspersed with shrubs, grasses, flowers, super diverse, as a really beautiful place. And right now they're gone. There are essentially no functional oak savannas left in the United States. They're the most endangered ecosystem in North America. And basically what happened is oak savannas create soil really fast. And really good, high quality, high carbon soil. And so every place where there was a savanna where it was plowable, it was burned and then plowed. There are a few spots in southwestern Wisconsin where I am. Actually, on our farm, we've got a hillside that is a relic oak savanna stand. Super high diversity. But any area that was not plowable got turned into forest without grazing animals and without burning. Our climate in the Midwest is very humid, and our climax vegetation is a mesic forest or a closed canopy forest. Silver or sugar maple would be like our climax species. So if you let area alone and our area go, if you take an old field and just let it go, it goes through succession, and it does not go to savanna. Savanna is not a natural state in our area. It goes into forest. So this is a big deal, and a little bit ago, a bunch of scientists from all over the Midwest came together because oaks are not regenerating. So we're losing our oaks for a lot of reasons. Management, deer is a big problem, but we're losing our oaks rapidly. So they all got together and like, what can we do about it? And this was like their take-home message was we need to restore all natural ecosystem functions and processes, including a natural range of biotic community types and conditions in which natural selection can operate. What's the most frequently used word in that paragraph? Natural, nature. Yeah, I think that's kind of the problem. So we have this myth in our culture that North America, before us white people got here, was somehow this like wilderness area that we conquered the wilderness and we tamed it and we established, colonized it. Most of us in this room, if we're here, we probably recognize that that's not true. This place was highly populated by a lot of people and very intensively managed. So I think of First Peoples here as the ultimate sort of keystone species. That really structured, they're the reason why we had oak savannas everywhere. If there weren't humans here, there would not have been oak savannas here. So there was some major ways that they managed the land that I'm going to go through. One is burning. That was their kind of primary technology for land management and used it for hundreds and hundreds and hundreds of reasons. One main one being to control animal populations, herbivore populations, to be able to manipulate where they go based on when you burn, after you burn, you get a flush of really high quality, high protein grass that attracts grazing animals, bison and elk and deer in particular. So the use of fire was a major force in shaping the sort of pre-European ecosystems in North America. And hunting was another major component. We like to kind of talk about Native Americans as being very conservation practice-minded, but that's relative to our concepts of conservation, and that's informed by our wilderness myth, which they didn't have. And in fact, they actually hit herbivore populations pretty hard. They actually focused their hunting on the reproductive cores of populations. They were like over-hunting almost intentionally, but then they would do it for a short period of time and then leave. And at the meta level, it actually maintains a really healthy population, but at a local level, it's hard. But it had a major impact because hunting, the animals impact the vegetation. So secondarily, through their hunting activities, they're having major impacts on the vegetation. And then horticulture, we don't think about that a lot. Here on the left, they're harvesting wild rice. The natural range of wild rice is a couple hundred miles north of where we live. But when settlers first showed up, there was wild rice all over southern Wisconsin, northern Illinois, and places that wild rice really can't live now. They were actively bringing it there, cultivating it. It was a thing. They planted fruits and nut trees. There's a village an old Indian village outside of Green Bay that's surrounded by deciduous forests. It's like sugar maple basswood forest. And where these Indian villages were, there's oaks, hickories, apples, plums. They were planting trees intentionally, and these were their staple crops. This is a Pomo Indian here on the right, collecting acorns. Acorns were a staple crop for many people for a long, long, long time. And then I love this quote because it kind of messes with our idea of what conservation is. When people don't use the plants, they get scarce. You got to use them so they come up again. If we have appropriate regenerative harvesting techniques, we can actually enhance the viability of the populations that we're harvesting for yield. So the take home here with this sort of Holocene savanna configuration that was fire driven was that the cumulative effects of Native American management was to replace forested land with open grassland savanna. So it's really interesting. If you go back further in time, if you look back before the last ice age, we had savannas here. And not just here, not just in California, not just in the Midwest, everywhere, including like the Great Plains, which we think of as being just a plains, kind of treeless place. There were trees. So going back at least 20 million years or so, we've had there's consistent evidence of savannas being like the dominant ecosystem form. So how does that happen if the natural state in our climax vegetation is forest? How come it's all savanna? Well, it's because you've got mastodons and elephants eating trees, knocking them over, stripping the bark off, stripping the leaves off, and opening it up for grass to grow in the sun. So grass needs sunlight to grow. It can't really grow in the shade. And so what would happen so the mastodons were like these keystone species that were shaping the ecology by knocking down trees, opening it up, getting grass in there. But what grass does is it attracts grazers. And those grazers come in there and they can maintain it in that grassy form. This researcher in Africa, McNaughton, coined the term a grazing lawn, which is basically that herbivores through grazing, through pulsed grazing, like savory style grazing, actually maintain that grassland state, even if in their absence it would go into forest. And I say, so Pleistocene generally refers to the time, the last couple million years when there was it was going back and forth in glaciation periods, but these savannas were going way back beyond, 20 to 25 million years of savannas. So 25 million years, that's a long time. So that's the evolutionary context of all of our vegetation. All of the native vegetation, all the trees, shrubs, grasses, flowers, they all evolved in this context. Tons and tons and tons of animals. So here's a Pleistocene megafauna from like National Geographic or something. You know, lots and lots of big animals eating all with their own specialized niches. Mostly browsers. Grazing didn't actually evolve until relatively recently, like 7 to 10 million years. Were the first true grazers. I'm going to talk about that in a little bit. But and this Pleistocene megafauna, this is recent. This is actually a small proportion of what existed even further back. So there's way more diversity even back a few million years before this. So this is kind of a depauperate version of the megafauna. So we're talking massive numbers of people, massive numbers of megafauna in a wide diversity of types, big, small, and everything in between. So get into a little bit of ecology here because I find it really helpful to think about some of these things. The notion of alternative stable states. This looks like a graph. It's not a graph. This is not a model. It's not doing anything quantitative. It's a story. Okay? It's telling a story about the relationship between a couple different things. So in this example, there's two basic stable states that lakes in our region can be in. A clear water state, up here on top, clear water column. Light can get down, penetrate down to the bottom. You've got a lot of vegetation in there. Because there's so much light, they're photosynthesizing, they're making oxygen. The water is highly oxygenated, and it can support a super large diversity of fishes. 20, 30, 40 different kinds of fish, shellfish. There was 250 types of native shellfish in our area in these freshwater systems. But once you start putting phosphorus into these systems, they can maintain their clear water state because there's all these biological negative feedbacks that are holding it in that state. But then you push it too far with that phosphorus loading and the nutrients, and then it feeds algal blooms. And then when you get an algal bloom, it's called eutrophication, and that basically the algae consumes all of those nutrients and consumes the oxygen, and it kills everything else. And then that is a very stable state. So the point of this graph is that, or it's not a graph, right? It's a story. The point of this story is that it's not a linear thing going from one state to the next. So that you increase phosphorus and nothing happens, and then all of a sudden you switch into the eutrophic state. But then once you're in that eutrophic state, it stabilizes. There's negative feedbacks in there. The biology whatever biology is in an ecosystem wants it to stay in that ecosystem. So you get these negative feedbacks that hold it in that state. So algae consumes all of the nutrients and it consumes the oxygen and it doesn't let fish grow. So it holds it in that state. So you can back off phosphorus and go back to the amount of phosphorus loading that you had before when it was a clear water state, and it doesn't go back. You got to go way back. So that's kind of the point here. And another illustration that's helpful is kind of these ball and cup diagrams. So the ball represents the state. the ecosystem, so clear water or eutrophied in this situation. And as you change the context, as you push it one direction or another with, say, phosphorus loading, or it could be fire, I'll talk about that in a second, it changes the dynamics so that it's stable or not stable. So if it's sitting in a cup, it's stable. If it's not, we don't need to know. This isn't. What matters is that biology sets the context for the situation. So here's another situation where we've got, climate, greenhouse gas concentrations, and if we keep pushing the greenhouse concentrations, right now we're in this stable equilibrium. We have been since the last glaciation. Very stable climate. That's the only reason we have sort of civilization right now. But if we push it beyond a threshold, it flips into another state. What that state's going to be, we don't know, but it's going to be different from what we're at now, and it's probably going to be a lot worse for humans once it flips into that other state. So anyway, I just find this kind of helpful to think about how biology controls the situation. We tend to think of physics as controlling the situation, right? It's like more biophysics, but biology has a lot to do. So we can think about forests as a stable state. So closed canopy, so there's no sunlight reaching the ground. They're pretty wet because they don't let the sunlight down, so that the sun doesn't dry it out. They're relatively high nutrients and relatively low diversity relative to some other situations. Whereas a grassland is another stable state if there's a lot of fire. So if your disturbance frequency goes up, you push it towards that grassland state, then that becomes the new stable state, and then the positive or the negative feedbacks that hold it in that state, the openness, the dryness, it's super low nutrient, and a pretty high diversity because you've got all of this disturbance. Disturbance is related to diversity. So savannas are sitting right here in the middle, and the point here is that they're unstable. Nature doesn't really want to be in a savanna if you don't have large animals and you don't have a keystone species. They're going to get pushed in one direction or another. In our case, in the Midwest, it's forest. In a drier, more arid place, it's going to be like a scrubland. But this savanna, in the absence of big herbivores or whatnot, it doesn't really want to stay there. So this intermediate disturbance hypothesis, all it means is that species diversity is maximized when disturbance intervals are intermediate and randomized. So if you have really lots of disturbance, if you have fire every year or tornadoes every year, you're going to have pretty low diversity because there's only the most robust that can handle it. But if you don't have any disturbance, you're going to have a pretty low diversity because it's going to be only the most efficient biology that can handle that context that survives. So it's this kind of weird intermediate phase, and that's what all those animals are about in the savanna, holding it in that state because of that intermediate level of disturbance. So savannas are complex, they're diverse. Intermediate disturbance is crucial, and they're maintained by keystone species. So in the absence of keystone species, they're incredibly unstable. But when there's a keystone species managing, you find a stable equilibrium. So you can actually develop this stable state where the biology is keeping it in that state. There's a relationship there's a direct trade-off between efficiency and resilience. And this is where what we're doing as permaculturalists is, I call myself a farmer because I raise animals and sell meat, but what I'm actually doing is the complete opposite of farming. So what farming does is it takes an ecosystem that's diverse and it removes all the diversity except for one thing, and it maximizes the efficiency of the production of that one thing. So it's pushing way off to the left here towards brittleness with no diversity because that maximizes efficiency, right? So if you're in a market selling your product, you are incentivized to maximize the efficiency of your production to bring down the cost of production in order to compete in that marketplace, which means you're killing your ecosystem. So in some ways, I'm absolutely not a farmer. I'm the opposite of a farmer because I'm actually intentionally decreasing the efficiency of what I do. So I'm not producing cattle in an efficient way. I'm intentionally, inefficiently producing cattle. And that's in order because if I do it that way, then I can also produce tree crops. I can produce fruit and nuts. I can produce all sorts of other animals. I can have sheep and pigs and goats and chickens and turkeys. And if I back off on the efficiency of all those things, then I can have a system that's stable, that is producing lots and lots and lots of different things. Now, how does that work out economically is a whole different talk. that I'm not going to get into today, but in later this week we're going to talk about it. So yeah, agriculture is way down here, and we got to get away from that. So the kind of take-home message is that the savanna form of vegetation, these like grasslands with scattered trees, is an emergent property of ecosystems that are working really well. A highly functioning ecosystem that are maintained by keystone species. Like, they got to have keystone species. And these functional ecosystems cool the planet, and they cool them in a couple of ways. And one way that we don't often think about is just through photosynthesis. So, if you go out on a sunny day and you take the temperature, the surface temperature of the ground, and you go out to a road, it's going to be really hot. That asphalt is soaking up solar energy, and it's going to be really hot. But the interesting thing is that the more complex the ecosystem and the more highly functioning it is, the more photosynthesis, the more densely photosynthesis is happening in one given place, the cooler it gets, because what organisms do is we use resources, or what plants do is they take sunshine and they use it to create sugars, and that takes a lot of energy out of sunshine, and then they radiate the waste back as heat, but it's a lot less than it was originally there. So this I just pulled off of NOAA's website. This is just the last few months. This is the outgoing long wave radiation. So it's the heat that's being reflected back up into space from the biosphere. And the really interesting thing to note, so these orange scale, the yellows and oranges are hotter, and then the blues are cooler. So obviously, like, the poles are cold and the tropics are hot. But look at these areas right over the Congo, right over the Amazon, over Southeast Asia. Notice that temperature at the equator. So look in the ocean what the temperature is at the equator. It's the hottest on the whole map. It's right there in the middle of the ocean between two continents on the equator. But look over the continents on the equator. It's the same temperature coming off of the Amazon as it is coming off of Wisconsin. That's crazy. That's ecology. We need that. We need that everywhere. There's another way that ecosystems cool the planet, and that is through this coevolution of grazing animals and grasses. Grasses are amazing. They grow really deep roots, and they pump carbon from the atmosphere through photosynthesis into the roots, and then that can become stable, recalcitrant form of carbon sequestration. So all these deep-rooted plants on the right here are like prairie plants. So they're the warm season grasses, the C4 grasses. That's our native grasses. This one here on the left, that's a Kentucky bluegrass. It's a cool season grass. So cool season grasses are traditionally what's grazed in European systems, and warm season grasses are what was all over North America. And they have very different root systems, and so the impacts, the carbon impact of grazing them is very different. So what basically happens, and this is going to be review for a lot of you guys, but grasses photosynthesize, animals eat it. When animals eat grasses, the grasses' response to that, so grasses keep a balance between their above ground biomass and their below ground biomass, so their root systems kind of generally reflect what's going on above ground. So warm season grasses can get 6 feet tall. The earlier settlers said they were above the heads of their horses. So really tall grasses, they had roots that were 10, 12, 20 feet deep. And if an animal grazes that down to the ground, what that grass does in response is to slough off a bunch of those roots, and those roots then get grabbed by the fungus, by the mycelium, and it gets converted into soil organic matter, into carbon. So we have really high carbon soils as a result of a long time of coevolution of grazing and grasses. So grasses in like a savory style mob grazing system pump carbon from the atmosphere into a stable source. As long as you don't plow it, it stays in the soil. And that is a really potent way of cooling the climate. So this guy, Greg Rotalik, is a scientist in Oregon. And he's looking at the coevolution of grazes and grasslands. So 50 million years ago, we had forests, and these forests were low albedo, which means they absorbed a lot of solar radiation. They didn't reflect it, so they're heating up the surface of the planet. High transpiration rate, low carbon storage, and they were pretty dry because they didn't have the carbon to hold on to the water. What ended up happening about 10 million years ago is that all these megafauna that had evolved to eat forests, they'd evolved in the forest, they were browsers, they were eating forests. Now grasses had been around for a while, but they were kind of in the woods. At this point, around 10 million years ago, Horses were the first ones. They evolved the ability to eat grasses. Grasses are really hard to digest. It's cellulose. It's really hard to digest. It took a long time. They had to develop the right teeth and the right digestive system to be able to handle grass. But once they did, a whole bunch of animals learned that trick. Camels, horses, bison. They learned how to eat grasses, and once that happened, you start seeing this enormous buildup of deep, deep, high-carbon black soil. And those grasslands were high albedo, so they reflected a lot of sunlight, so it cooled, and they were high-carbon storage, and they held onto the moisture with all that carbon. So 65 million years ago, Paul this morning was talking about the asteroid that impacted in the Yucatan. It wiped out the dinosaurs. It wiped out most of life on this planet. It was like the reset button. Life had to kind of start over. The first grasses appear right away in the record, but they stay really small. They don't spread. They're just kind of in the shade of the trees. And these are the C3 grasses, the cool C3 grasses. It took about 10 to 12 million years for a mammal to evolve the size of a squirrel. So mammals had held on through there, the little mice. It took a long time. But then once they got to the size of a squirrel, like the arms race was on. And by 20 million years after that, we had rhinos, peccaries, beavers, rodents, horses, camels. The basic building blocks, the ancestors of all the fauna that we know, had all kind of either migrated here or evolved here. Forests started breaking up as these animals evolved to eat them, right? So rhinos, peccaries, beavers, these are all browsing, they're eating trees. So forests start to break up at this point. There were some major disruptions when Antarctica split off from Australia. That's kind of irrelevant right now. Interesting to me because I love oak trees. Squirrels and nut trees start their coevolution at this point, and we see deciduous trees, which had been relegated to the North Pole for a long time. That's where deciduousness evolved. They start spreading out into areas that had formerly only been occupied by conifers because of squirrels. That's pretty cool. We had lowest mammal diversity. Notice the climate. So this graph here is temperature, is mean global temperature. So as the ecosystem is evolving out of this destruction of reset event 65 million years ago, it gets warmer and warmer and warmer, and then once the animals start evolving, once they start developing more complex ecosystems, the climate's going down, 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 down. There's some severe disruptions with some severe droughts and cooling periods. We lost a lot of mammals, kind of had a bit of a crisis there. Temperatures went back up, but then things started getting crazy when teeth evolved to eat grass. It changed everything. Within a million years of that evolution, we see the spread of grass-dominated ecosystems, grasslands, started spreading over all of the continents, North America, South America, Africa, Asia. We had a peak mammal diversity right about that time, and then the climate just started taking a nosedive. Once we got that evolution of grazers and grasslands, we started developing these high carbon soils. We were rapidly sequestering carbon out of the atmosphere. At this point, 5 million years ago, we're down to like 280, 250 parts per million carbon, really low carbon. So C4 grasses evolved at this time and started spreading. C4 grasses is a different photosynthetic pathway, and it uses carbon more efficiently. It evolved in 60 different plant communities independently at the same time in response to a low carbon atmosphere, and they spread over the planet, and that was a positive feedback. It made it get cooler and cooler because these are the ones with the really deep roots. So up until then, it was C3 grasses. They were doing the whole carbon sequestration thing, but when the radiation of C4 grasses happened, it got kicked into high gear, and I wish I had a little pointer right there. These are the ice ages. So this is the last 2 million years when we fluctuate between ice ages. So, we can thank grazers and grasses for the ice ages, and I can't wait for the next ice age. So we need to cool this planet. We've destroyed all those ecosystems that have been cooling us for a long, long time, and it's my opinion that we need to get them back. We don't want to go into this runaway heating scenario. I don't know about you, but I like Earth. I don't want to be on Venus. But to get there, we got to restore our ecosystems. So I studied restoration ecology, and I did restoration ecology. And what restoration ecology means in the Midwestern United States is you herbicide any plant that's not native, and you help the plants that are native. So as restoration ecologists, we were basically, proponents of Monsanto and Dow. We were spraying their chemicals all over exotic invasive plants. Think about an invasive plant. So in the Midwest, it's shrubs for the most part that we consider invasive. They come over and take over our woodlands. What I talk about, all these plants evolved in the context of heavy browsing from animals. They're just expecting elk and horses to come through and graze them every once in a while, and because they don't happen, they go invasive. We just need animals managing the landscape, is all it comes down to. So if we want functional ecosystems to cool the planet, those ecosystems need keystone species. It was the mastodons for 17 million years. Humans killed all the mastodons. Indians became the keystone species managing with fire, so we've been in this progression of, we're talking about the sixth extinction this morning, call was, and how we're losing diversity. It started with the loss of the megafauna. That was like the first ecological catastrophe, almost arguably of higher impact than what's going on right now. But the Indians took over and they actually managed the landscape, which we don't really do. They managed the landscape, but they used fire, which is a homogeneous grazing, right? It's like grazing, it's doing the same thing, it's keeping it open, but it's non-selective. So what ends up happening is it's a more homogenized vegetation and much less diversity overall. Although relative to our ecosystems now, those are way more diverse. The Indian managed, burning, created relatively diverse ecosystems to what we have, but relative to what was before, low diversity, interestingly enough. So we've got to become keystone species now. Like, we sort of are already, but we're keystone species of ecosystems that don't work. I mean, a cornfield, a wheat field, these are, they are an ecosystem. There are plants there. We keep it in early succession. We keep the disturbances happening every year by plowing our herbicide, and we wouldn't be here if we weren't trying to come up with a solution to that problem. So we've got to become keystone species. So the next few slides are going to just kind of talk about what I think we kind of should be doing as keystone species. This is a cornfield I took out of production this year and planted a big mix of these, C4 warm season grasses and flowers. And then this spring we're going to be planting a bunch of trees there. But anyway, I'm going to go through this fast because you guys know all this stuff already. This is just permaculture, right? We plant and tend fruit and nut trees and vines and shrubs. We manage vegetation. This is Mark and Jen Shepard's son, Eric. We got a scythe when we were there just, playing around. We hand him this scythe and he goes out for like 8 hours. And the dude is like a machine. And it was like a putting green. I mean, the guy was like, had perfect form. It was impressive. It was impressive. But that's a lot of work. I don't want to do that. I don't want to manage vegetation with my hand and hand tools. I want to use animals. We really need to use animals way more. We don't need fire. We don't need to oxidize more carbon up into the atmosphere like Savory was talking about last night. We need to get that into the biomass of animals. We need herbivores to manage vegetation. We need to be breeding. Like we're starting from scratch. Like we have a long way to go to be developing high quality, robust, disease-resistant, vibrant, locally adapted genotypes of oaks and hickories and all of these things that we know we're going to need for the future. We're just scratching the surface of that. We got a long way to go. And of course, we've got to enjoy and share the abundance. Cows really like apples. That's why I'm planting a lot of apple trees. So that's like the material things that we need to do to become keystone species, I think. But that's like the easy part. The material on the ground thing, that's kind of the easy part. Some of the harder things are more internal and social. So like in my generation, I moved around a lot. I'm 32 years old, I've lived in 27 different places, okay? Different houses. I bought land, I built a house, and I'm never gonna leave. And I think that that's really important to make the decisions that we need to on the land. I think there's a lot of attractiveness to a cosmopolitan, mobile, nomadic lifestyle in my generation. And there's nothing wrong with that. And I think there's a lot of personal growth that can happen through travel and all that kind of stuff. But I think at some point we gotta settle down and get serious. We gotta rewild ourselves. So we think of ourselves as Homo sapiens. We're Homo domesticus. I don't know if you realize. Can anybody tell the difference between a Chihuahua and a wolf? I think we've we're rapidly degraded our DNA and our culture, and so I don't know where we need to, how we're going to do this, but I don't know about you, but I feel like our culture is kind of messed up, and the way we think about the world is messed up, and our language is messed up, and our vocabulary is messed up. We need a different way of being, and one way to get there is to just eat animal parts and forage greens and mushrooms. This is actually kind of funny. I had a lamb that got stuck in an electric netting fence. A friend of mine came over and was chatting with me, and I went back to check on my lambs after he left, and boom, we had a dead lamb. Got buddy Ben Falk up in Vermont was visiting that day, so we ate the lamb. So this is a really big point, and this is one of the things I'm talking about. What our current culture, and especially in our approach to land management, and especially in our approach to agriculture, we've got to simplify things so that we can understand them. That's what science does. It removes variability so that we can understand things. And the more I learn, the more I realize that I don't know what's going on. And when I'm sitting around at my farm, I get overwhelmed quite often at my lack of understanding. And what I have realized is that almost all the concepts that I had coming into farming, whether they're permaculture concepts, academic concepts, ecological concepts, a lot of them are really powerful, and a lot of them really can be really quite helpful, but a lot of the more powerful concepts hide as much as they illuminate. And I think it's really important to embrace the uncertainty of all this. I mean, savannas are complex systems, we as humans are complex systems, our social structures are complex systems. And what I mean by complex systems is something we can't quite understand. It's something we can't model. We can't predict what's going to happen. And we've got to embrace that mystery because, and approach it with humility. And we're not going to figure it out with our brains. There's other ways of knowing. And I really liked what Paul was talking about this morning. And that really resonated with me because I feel like I learn the most when I erase all the concepts in my head and sit next to an oak tree and let that oak tree tell me something, or I sit next to my cattle and let them tell me something. And I think we've got to open ourselves up to alternative ways of knowing. And I say that with a background in science. So I get the science thing, I'm all for it, but there's other ways, and I think to get to the next level of being human, we've got to learn new ways of knowing. Another big thing is we can't do this on our own. I can't do this. We bought 100 acres. I'm out there planting trees and raising animals, and it's a lot of work. And I don't think I can pull it off by myself. And I think it really as humans, we lived in small, tight, intimate communities for 99% of our existence. And it's only in the very recent past that we diverged from that. And I feel like we either have to live in a dense urban area, or the only alternative model is the hippie back to the lander thing, where we go and homestead on our own and prove our pioneer masculine awesomeness. But there's got to be a middle path, right? There's got to be another way where we work together. And so I think a big part of that is sort of intergenerational collaboration. So we bought our land in partnership with my wife's parents. They just quit their jobs in the city. And are building a house eventually on the farm, moving out. We've got 100 acres. I don't really need to manage 100 acres to feel good about myself or to stay sane, actually, and I would love to have more people around. There are lots of legal reasons why that's really difficult, but that's a whole other presentation. Well, I'll talk about actually that tomorrow or Saturday. But it's going to take us getting together and working together. So, find your tribe, because that's the way that stuff is actually going to happen. So we've got 100 acres, and that white not square. It's a S shape, which, anyway. All the land around us is for sale, and it's really cheap. So, we're looking for neighbors that are cool. We want to start a village. It's going to be awesome. We're teaching a course this summer for those of you that might be interested. Me and my wife. My wife is the homesteader extraordinaire and accountant. We've got limited partnership that owns the land. We've got 2 businesses. She does all the taxes, all the accounting. She's going to be talking about that. Mark Shipper's going to be there talking about his place. We'll spend some time at New Forest Farm. Grant Schultz is coming down. Keyline GPS. Lindsay, cold climate permaculture extraordinaire. Dana Burtness talking about marketing and doing the direct market thing. Brandon Bless is an instructor for Sterling College. He teaches restoration agriculture. He's going to be coming down. It's going to be a lot of fun. That's all I got. Any questions?
talking about the phosphorus loading. What's the historical source of phosphorus loading? Obviously now it's like fertilizer runoffs, but were there historical sources of phosphorus loading that tended those clear water systems to go eutrophic?
We go like pre-humans, or like without humans, or?
I'd say post-humans, but pre.
So lakes are ephemeral. They eventually get sedimented in and go eutrophic, and then they turn into like a bog. That's like the natural progression. So it's like humans facilitate a premature death, a premature phosphorus loading. And so I went to graduate school in Madison. Madison is surrounded by 3 lakes, or 4 lakes. And when you read like the historic records, like the first white people coming in there canoeing around, and it's like you could see all the way down to the bottom, 60 feet. And plants and fish, and like there were Native American communities there, big buffalo fish. Actually, interesting thing, when you've got that clear water system and a lot of fish, one element and one way that humans were keystone species was by eating fish and crapping up on the hills,
like bears,
removing the phosphorus. And so there was phosphorus removal mechanisms built in. Birds, waterfowl do the same thing. Interestingly, in Madison, they started, this little, European village right there, and in 1860 is when the first white people started living there. By 1880, it was already eutrophic, and they were already complaining about the algae and the smell. All the sewage was going right into the lakes. Actually, Madison, as a progressive liberal place, didn't stop putting raw sewage directly into the lakes until 1955. 100 years of, shitting in your water.
Human waste was the source.
Human waste, right? And then by the time they removed that, but by the time they developed, mitigation strategies for that, not dumping directly into the lake, we have big scale ag, and now it's a non-point source and much harder to deal with.
Peter, repeat the question too.
Okay.
Yeah.
Yes. The question was, how did phosphorus loading happen before? Yes.
First of all, thank you. This is just amazing. But when you were saying there's this trade-off between efficiency and resilience, I had this knee-jerk reaction of, say it ain't so. It's like, if you accept that reductionist view, right, that the only thing that you're producing on a farm is cattle, then yeah, your argument holds. But have you done numbers of like calorie production or another metric that would allow you to capture more and like measure the production on a farm like yours, which is quote unquote inefficient versus a more traditional?
So the question is, have I looked at other metrics besides economic? Would that be fair?
Or a broader
money?
economic metric, right? Because if you're having more than one output, you can sell all of those and turn them into money.
Right. So my response to that, so the question is, with the whole trade-off of efficiency and resilience, what are other ways to look at it, basically? Because obviously, if you're producing a whole bunch of stuff instead of just one thing, there's more yield to be had, and that's true. I mean, the data. You can definitely produce more calories, definitely produce a lot higher quality calories. That's for sure. The key, though, is if you are marketing your product in a market with conventional growers. So if I'm growing beef and I'm selling it at the sale barn with everybody else, I get the same price. So the point is that my cost of production for every one thing is going to be higher. Harvesting is going to be less efficient in a diversified polyculture than it's going to be in a monoculture. So you have more resilience, but in your day-to-day operations, you're going to be less efficient at harvesting, at everything else. Now your input costs approach, go very, very low. But the point is that it's difficult to compete head-to-head with somebody who is following the efficient side of production and willing to do that. Yeah?
But that's not to say that you couldn't create another graph that says lifestyle versus resilience or efficiency and show that with a diverse system, you'd have a better lifestyle.
Absolutely. So that's the lifestyle thing is huge, and that's why we're doing it. I mean, it's much of a reason why we're doing what we're doing as anything else. But I think the key here, the pattern, the takeaway message is that as land occupants, we have to generate income from our land-based activities, But the more we can accept a return for our time and energy in non-monetary value, the better off we're going to be. The more ecology we're going to be able to facilitate happening, the more we require to be paid in cash, the more we're going to be forced down the efficient pathway and start sacrificing the ecology to make that return. So, you know, yeah, I'm willing to, like, all I want is to restore our watershed and to have cool neighbors, and whatever it takes to do that, I'm willing, but I don't need cash, right? Like, I'm willing to accept my return, my income, in the ability to have the best food on the planet and to be able to walk around the most beautiful place in the world every single day and drink water that's bubbling up out of the ground, that's not chlorinated. I come here, my digestive system's screwed up. Come in here, man. This food and this water is nuts.
Do you know anything about oak wilt in general?
Yep.
Coming in from Texas, and there's a lot of problems like oak wilt.
Yep, so the question is about oak wilt, which is a disease that hurts oak trees in general. There's a lot of that in our area. It tends to impact trees that are already stressed. So healthy trees tend not to get oak wilt and die, or they'll have the wilt, but it won't necessarily kill them. But then if you go into a housing development where, you know, they're bulldozing, digging foundations, they're hurting, you know, hitting the roots of the trees, those are the ones that end up getting the wilt and dying from it. So I don't see as too much of an issue for us as long as we allow those trees to live in a really healthy context. Yeah.
When you bought your land, did you do a plan for developing the property? And if so, are you doing it in bits and pieces, or have you gone in and done key-line design on it?
So the question is about planning, and when we bought our property, have we planned it, and how are we doing it? Are we doing key line design? I was just joking, another farmer friend of mine last night, we were walking around outside, and there's all these really nice looking diagrams with trees and, you know, maps, and it's like all super like laid out and designed. And he's like, hey Peter, do you have a map like this for your farm? And I was like, no, do you? He's like, no. I'm flying by the seat of my pants, honestly. I have a design in my head, you know, but this is kind of a bigger conversation, I think. But I think it's really important, especially in the permaculture world, because there's a lot of emphasis on design in the permaculture world. I don't really think that I think the landscape knows what it wants and what it needs, and that it's our job to tune into that and make that manifest. And I don't think that happens on a computer screen off your land, basically. I think that happens, it's an emergent process of being on the land itself. So when I bought the land, I thought that I knew what I wanted to do. I thought I had a design. I made a bunch of maps on Google Earth, some key lines here and trees here, roads here, this makes the most sense, but it was all in an intellectual way. It was like, this makes sense in a rational, intellectual way. And a year later, it's like, I'm not gonna do that. Maybe some of those things will actually happen. I'm gonna do stuff. We're gonna do swales in a few places where I think it makes sense. A lot of places, we have really sandy soil, it doesn't really make sense in a lot of places. Up on the ridge, it does. You know, we're planting lots and lots of trees. You know, we're going to be intentional about how we plant them. The cornfield eventually will be doing some haying. So, you know, considering you know, equipment widths and all that stuff, that'll definitely go into it. But, you know, I don't have a grand master plan. I'm trying to just pay attention and do what's right.
So how much did it change from what you thought to what you're actually experiencing?
I can't answer that because I don't know exactly what I'm going to do. Part of the problem is that this property is incredibly complicated. In 100 acres, we've got hillsides that face every single direction. We've got ridgetop clay soils. We've got bottomland sandy soils. We've got springs and streams, riparian, and it's really steep hills. So like machinery, most of my property I can't ride a tractor on. So I'm limited in a lot of ways, and a lot of my designs, a lot of the plans are just going to be more localized. So, you know, a swale from here to here to mitigate a specific problem. that will inform the larger design, but it's a work in progress. I don't know how to answer that question. Yeah.
You alluded to the oak savannas of California.
Yep.
Which are a little more brittle or dry.
Yep.
Dry leaning to your fire.
Yep.
Have you put much thought toward the differences of the two, kind of like the ecological differences and how it may inform different establishment and maintenance practices and stuff? Have you got that far?
I have not thought too much about it just because I haven't spent much time here in California in this biome, so I'm not super familiar with it. I think that there's a lot of generalities in savannas, especially with the use of animals, that make sense across contexts, but more specific than that, I haven't put a whole lot of thought into. One interesting thing to note though, especially like in the Central Valley, the Native American communities there, like they were not practicing agriculture, yet they had population densities that were the same as agricultural communities elsewhere, which just speaks to the incredible productivity of these ecosystems. I mean, it's just mind-blowing. Yeah.
I love what you have to say about kind of availing the whole mind of your site, because there are multiple ways of doing it, as you said. Building on that, I have an intuition that I work with cattle in the oak savanna woodland, Northern California area. I have an intuition that these old trees that are 30 plus years old are probably benefited from the animal impact, so not just the understory, but the trees themselves, their root system, et cetera, all the way through. I was wondering if you had any insight on that.
So the question is, you know, the impacts of animals and large animals on the trees, and I have the same intuition. I don't have any hard data to back anything up, although it was really interesting, well, you know, at Mark's place, you know, we had a bunch of pigs one year, and well, every year, you know, there's pigs, and pigs love to scratch their butts on things, and so do cattle. All big animals do, but pigs roll in the mud all the time, and then they scratch their butts on things, and it seals the base around trees with mud. So in the apple orchard, where you've got these big apple trees, the pigs are scratching their butts and sealing with mud, caking mud on a rim around the tree. And so there's a lot of things that does that helps pests. So a lot of pests, traditional apple pests, can't climb up the tree. And it's really interesting in biodynamics. They actually make little mud concoctions and then paint it on the trees. Again, if you can find animals to do your job for you, you're going to have a better time. So I don't have anything more than that. I intuit the same thing. I mean, I've got two hawthorn trees that, or one in particular, that for some reason my cattle will walk a half mile out of their way to go scratch. They'll pass 20 other trees and go scratch on this one hawthorn tree. I don't know why. You know, it's something magical about this one tree, but they reliably do it every single day.
I was wondering if you could point in the direction of some resources describing that process of the genesis of these savanna systems, how they were evolving over your million-year cycle presentation.
Resources about the genesis of savannas. I've been putting this together from a wide range of resources, but I've never seen anybody make these points about just like the whole story. So it's like little bits and pieces here and there. So, you know, one would be a book called Mega Herbivores by Norman Owen Smith, an African biologist. It's an excellent book. He talks about the big rhinos and elephants in Africa and their impacts on the ecosystem, and then he makes some generalizations about what that must have meant in a megafauna-dominated world. So that was a big influence for me, for sure. Some of the historical stuff, well, that's one source because he does kind of go back. But man, there's not much. There's some paleo, the paper that I cited in there, Greg Ritalik, talking about the grazer grass coevolution. That's all brand new, you know, papers just published like this year and last year. So you can check that out. And the citations for all that are in the PowerPoint, which I'll make the slides available if you want to access that. Yeah?
I have a question about the periodicity of fire in the natural savanna landscape.
Natural meaning?
Well, I mean, I know the emergers were lighting fires for their own purposes, but so maybe before that in comparison to maybe a more increased periodicity of fire, once it was being utilized by
So,
humans?
so prior to, so the question's about fire and periodicity and pre-humans, what was happening with fire. In the Midwest, at least, I can't really speak to anywhere else. Pre-humans, there was the megafauna, so we didn't have this buildup of vegetation that would lead to fires. And also, in the Midwest, because it's so humid, the only other ignition sources would be lightning. But in our climate, lightning comes with thunderstorms, a lot of rain. So they're not very good at starting fires, unless you've got a lot of vegetation already built up, in which case it can happen. It's not like the West where you get those like intense lightning storms that don't have water. Our storms almost always have a lot of water. So there's not much fire outside of Native American lit fires for a long time. Yeah, question in the back. So the question is about metrics and if there are other sources other than carbon for evaluating what they would call a non-monetary ecosystem, like an ecosystem service. I think one issue is that we're talking about really complex ecosystems and there's so much going on. When I'm talking to people, like what I want to do is just get them out on the land and say like, look around, because I feel like we can intuit a lot of those ecosystem services just by observation. But then if you want to communicate that with others, quantifying it, it's really difficult. You can do, above ground carbon, you can do, soil carbon. It's really, ecosystems are really heterogeneous. So it's really hard to generalize and say like, on this 100 acres, we've sequestered this much carbon in this much time, or, we've increased the water infiltration this much. I've done some preliminary, vegetation surveys. So at some point I'll be able to say like, well, we started off with this level of biodiversity and now we're here. But even that, it's really complicated. And it's really, to get accurate numbers for anything like that requires a whole lot of work. It's a really data labor intensive thing to collect data, especially in a complex landscape like I live in, driftless area, unglaciated. So it's, we still have all of our landforms. We didn't get plowed over. It's not flat. And so it's really complicated. It's really heterogeneous, and so it's really hard to generalize, like on this 100 acres we did this, 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 and this. So those are my thoughts, but I don't have any, if anybody else has any answers. I think we're out of time, so thanks everybody.